Hello, geometers. This is Miss Backfish, and I am here to talk to you about similar solids. Let's remember that similarity is something that means that we have basically the same shape, but probably different sizes. However, the change is proportional. In other words, whatever the ratio of the lengths are is the same for the ratio of the widths or the ratio of the heights for these two rectangular prisms that you see here. That would make them similar. So what I want to do first is dive in and explore this a little bit, because this is me telling you about a relationship that you don't have to take my word for. You can figure it out for yourself. You can just as easily figure this relationship out by exploring some of the things we can find with geometric solids, which means basically three-dimensional shapes like prisms and pyramids and cylinders and spheres and cones. So the first thing I want you to do is go ahead and pause this video, and you're going to find the two things that you are asked to find here. First off, the area of the base, and we just mean one base. So in other words, like this area on this cylinder and this area on this cylinder, and also the volume for each one. So pause your video now if you haven't already, and go ahead and make sure you can figure out the area of the circular base for each of those and the area of the volume of the entire cylinder. Okay, so hopefully you've got those now, and I'm going to go ahead and catch up with you. Both of these have a circle as the base. That's what every cylinder has. And if we want the area, we're talking about pi r squared. So pi r squared when r is 4 looks like this. Pi r squared when r is 5 looks like this. All right, so that was step one, was to find the area of the circular base for each of those. Next, we want to find the volume of each of our cylinders, and I want to remind you that the volume of a cylinder is the area of the base, which is pi r squared, times the height. So for each of these two cylinders, we're going to do pi r squared times the height. So for the smaller cylinder, the height is 10, the r is 4, so that's pi 4 squared times 10. 4 squared is 16. This whole part really is just what we got here. Times 10 makes it 160 pi. For the larger cylinder, we have pi r squared, same thing that we had here, times the height here is 12.5. So times 12.5. And I need to get my calculator out for that. So 12.5 times 25 gives me, I'm going to go ahead and leave this with the pi, even though usually we don't have decimals when we're dealing with exact form. But there was a decimal given in the problem here. So I'm going to leave it as a decimal, but I still want to leave it in exact form for reasons I'll show you in a little bit. Okay, so you have done that. And now what I want to do is compare. I said that these were similar figures, or I didn't say that about this, but you knew where I was going with this, right? So similar figures, remember, are proportional. In other words, if this is 4 to 5, looking at the radii, radius here is 4, radius here is 5, relationship of 4 to 5, then this should be 4 to 5 as well. Okay, is it? 10 over 12.5. Does that simplify to 4/5? It does. One way to check it, other than using it in my calculator like that, would be to say, does 4 over 5 equal 10 over 12.5? And we could cross multiply. 4 times 12.5, that's 50. That's 4 times 12.5. And 5 times 10, also 50. So yes, those are equal. That is a true proportion. So yes, these cylinders are similar. Similar. I'm kind of dancing around a tongue twister. So what is the similarity ratio here? Well, let's look at the radii. Okay, here the radius is 4, here the radius is 5. The similarity ratio, that 4 to 5 that we got on the calculator, that's just the simplest reduction of a fraction of the lengths, a comparison of the lengths. In other words, if I do 10 over 12.5 and simplify that, I'll get 4/5. This time I actually have those numbers, 4/5, 4/5. So my similarity ratio here is 4:5. So this is a 4:5 ratio. Let's go ahead and say 4:5. That's the ratio of my radii. That's the similarity ratio, the ratio of my radii. It's also the ratio of my heights. It's the ratio of basically any straight objects there. So 16 pi over 25, also 4:5, right? 16 pi over 25 pi. Let's type it as a fraction. What's going to happen to the pi's here? Pi's cancel, right? And it doesn't reduce any further. That doesn't reduce. So the simplest form of the fraction comparing this area to this area is 16 to 25, not 4:5. Okay. What about the volumes? Well, let's see what happens when I compare 160 pi to 312.5 pi. The pi's will cancel. Let's change that back to a simplified fraction. That's 64 over 125. Now we can write it as a ratio like this with the little colon, or we could also write it as a fraction. Either way is fine. Okay, so I'm going to set that aside first in a little chart and then go explore another example. Okay, so here's my chart. I'm going to put this information again. Remember, or put the information in. Again, we remember that the radii had a ratio of 4:5. The base areas had a ratio of 16 to 25, and the volumes had a ratio of 64 to 125. So that's the information I'm going to put in my chart. 4:5, 16 to 25, and 64 to 125. Okay, now I'm going to look at another example. Okay, here I have two pyramids I have drawn, and they just so happen to be similar pyramids. How do I know they're similar? Well, let me just compare 6 to 8. Let's see, where can I put this calculator? 6 to 8, that's 0.75. What about 3 to 4? We know that's also 0.75. What about 12 to 16? Those all give me the same decimal because they're all the same ratio. They're all 3/4. So these are similar pyramids because I said so, right? Okay, we're going to do the same thing we did in the last one. We're going to find the area of the base. In this case, we have a rectangular base for each of these pyramids. And we're going to find the volume. So again, pause your video. Go ahead and do those. Come back when you're ready to go. Okay, ready? Let's get going. First off, I'm going to compare just some article of length, some item of length. And let's just do the heights. Those are easy to identify. So let's compare my heights. And actually, I trimmed my paper so I had a little bit more room to write. So my heights were, small pyramid has a height of 12. Large pyramid has a height of 16. Ratio 12 to 16 simplifies to what? 12 over 16. As a fraction, that's 3/4. So I'm going to go ahead and say that's a 3 to 4 ratio. Now, if you compare ratio of lengths, corresponding lengths, like for instance, the height, it's a length. In other words, just a distance, a linear distance or lineal distance. Any of them, you get the same thing. 3 to 4. 6 to 8 is 3 to 4. This is the similarity ratio. Okay? Sometimes people call it the scale factor. I don't necessarily like to combine them that way because to me, scale factor says that we're dilating. But if you're looking at this, if you're looking at a worksheet and it asks you what is the scale factor of these two things, generally that's saying it's asking me for the ratio, the similarity ratio. Okay, so that's the height. Let's look at the area of the bases. The bases here are rectangles, so that's going to be length times width. It's area of the bases. So here, this little guy's base is 3 by 6, which is 18. And this guy's base, I don't know why I made the male, 8 by 4 is 32. Okay, so that's the area of the bases. What kind of ratio is that? Well, 18 over 32. You could simplify it the good old-fashioned way. And it's basically 9. In other words, let me grab a sheet of paper here, sorry. When you want a blank one, 18 over 32. We can say what goes into both of them? 2 goes into both of them. 2 goes in 9 times, 2 goes in 16 times. There you go. 9 to 16, a ratio of 9 to 16. Not 3 to 4. And finally, the volumes. The volumes of pyramids, the volume formula is 1/3 area of the base times the height. Well, conveniently, we just found the area of the base. So we're going to incorporate that. So 1/3. For the small one, the height is 12. The area of the base was 18. So 1/3, 18 times 12. Third of 18 is 6. So 6 times 12, that is 72. And then over here, 1/3 area of the base, which we said was 32, times the height, which is 16. So that's not going to be as clean and nice. 32 times 16 divided by 3. Same thing. Multiplying by 1/3 is the same as dividing by 3. So I get, I don't know if I like this. Let me think about how I want to write this. Okay, I decided to go with it as a decimal. It might show what I'm trying to show a little bit more cleanly if I were to use fractions, but I don't want anybody getting hung up on the fractions. So I think it will still serve its purpose. By the way, if you hear beeping, that's my projector. It makes weird noises in the afternoon. So let's see what ratio this is. Okay, so 72 divided by, and I could type that in, or I could just say answer, and I get 27 over 64. So that's my ratio. 27 to 64 is the ratio for the volumes. Again, it's not 3/4. So let's go to our chart and fill this information in. Okay, first thing I want to point out about my chart is that this word doesn't really apply to pyramids. We compared the heights, not the radii. Okay, so I'm going to say the heights. And then we did compare the area of the bases, and then we did compare the volumes. So for the heights, we got 3 to 4. For the area of the bases, we got 9 to 16. And for the volumes, we got 27 to 64. I know that some of you are seeing the pattern here. Okay? So here's basically where we're going with this. This column, this is my ratio of lengths of, and I'm going to use a sort of an oxymoron, but straight lengths. In other words, straight units. Things like inches, feet, miles, centimeters. Anything that can be measured in just plain straight units. Not square units, not cubic units. It's just my measure of lengths. So we're just going to say the ratio of the lengths is what we're looking at here. Okay? And we already said that's going to be the same as the similarity ratio. And if they're using the term loosely, your scale factor. Okay? Next, areas. Okay? In this case, we've run the areas of the bases. But I'm just going to say, let's make this a little more generic and just say these are representative of ratios of areas in both cases. True? True. And finally, our last column, that was representative of the ratios of volumes in both cases. So what do we see here? Well, whatever my length ratio or similarity ratio is, let's call it A over B. How do 16 and 25 relate to 4 and 5? Well, that's A squared over B squared. Also could be written like this, A over B all squared. And then for volume, if A is 4, 4 times 4 times 4 makes 64. 5 times 5 times 5 makes 125. This is cubed. A cubed over B cubed. Or we could write it like this. Same thing. Same thing happened with the pyramids. If we had, let's use different letters, but usually we use A over B to describe these. But let's go ahead and just say, if this is my M over N, okay, then M squared would be 9. N squared would be 16. M cubed would be 27. N cubed would be 64. So whatever your similarity ratio is, or your ratio of just a pair of corresponding lengths, and that could be a radius, it could be a height, it could be a slant height, it could be a width, any just plain straight length, corresponding ones. In other words, it has to be the same one on each figure, the ones that would go together. Whatever your similarity ratio is, the length ratio, if you square it, you get the area ratio. If you cube that, you get the volume ratio. To me, the easiest way to remember this is to think about units. Let's pick a unit, centimeters. I would measure length in centimeters if that's what I'm using. What would the area be if I'm using centimeters? Squared centimeters, just like this is squared. What would volume be in terms of centimeters? Cubic centimeters, just like this is cubed. Okay, so for instance, if you are told that the similarity ratio of two, let's say they are, how about rectangular prisms? Is 2 to 5, then we know that the ratio of any areas associated with those rectangles, with those prisms, is going to be the square of that. For the area ratios, we square the similarity ratio. The way to square a fraction is just square the top, so the 2 squared over square the bottom, 5 squared. And again, if the similarity ratio of two rectangular prisms is 2 to 5, then the volume ratio is 2 cubed, and let's go ahead and write it that way. 2 cubed over 5 cubed, which is 8 over 125. It's a pretty cool relationship, actually. Now, we do need to talk for a second about area if we're using things like cylinders and pyramids. I chose to talk about the areas of the bases. Okay? One of the things we have not talked about in our unit, because we only hit volume in this unit, is surface area. And so what I want to point out to you is that this relationship about areas, that if we have this similarity ratio, then the area ratio is this, and the volume ratio is this. This is any kind of area, whether it's the area of the base, or sometimes you'll be told something called lateral area, or you could be talking about surface area. Quick glimpse at surface area. Okay, here we have a cylinder. It's just a video I found on YouTube, and it's unrolling so that we can see all the surfaces that go into making that cylinder. All right, so what we see when we have that cylinder kind of unfolded is that we can see it's made up of a rectangle and 2 circles. Those are the surfaces, and the surface area would be if I found the area of the rectangle, the area of the circle, and I added them all up. That would be surface area. okay? Here's one that animates the surfaces of a rectangular prism pretty well, okay? The colored spaces there, those are your surfaces. So the surface area would be basically if I took the area of the blue rectangles and I added them plus the area of the orange rectangles plus the area of the yellow rectangles. Those are all the surfaces. Now, if you're in my class looking at this in this particular unit, in this particular year, we're just doing volume, we're not doing surface area. So you don't have to worry about how to find the surface area, although I'm sure you've done it at some point in the past. I just wanted to remind you what it meant so that it was not an intimidating thing to hear. Okay? It's just another type of area that could be associated with our three-dimensional figures, meaning the area of all the surfaces. The thing to know here, though, is just whatever your length ratio is, when you square that, you get the ratio of any areas, whether it's the base areas, whether it's the lateral areas, whether it's the surface areas, anything related to flat area, basically, or anything you would use units squared on. Okay? Okay, so let's try an application of this, of what we've looked at. This says the scale factor of two solids is 4 to 9. The surface area of the smaller figure is 192 square meters, and the volume is 1,536 cubic meters. Find the surface area and volume of the larger figure. And there I took out the stray S on figure. All right, so my scale factor, which really means similarity ratio. The similarity ratio of my two solids is 4 to 9. Okay, so that's the length ratio. So that's how I'm thinking this through. I'm thinking, okay, they told me 4 to 9 was the length ratio or the similarity ratio. If the similarity ratio is 4 to 9, remember this is like my A to B, then the area ratio for these guys would be 4 squared over 9 squared. A squared over B squared. The volume ratio would be 4 cubed over 9 cubed. I don't remember what that is off the top of my head. That's horrible. 729. Okay. All right. So that's A cubed over B cubed. Now, what that means is if I'm doing any kind of problems that talk about area, including surface area, then this is the ratio I use to compare the two figures. If I'm doing anything to talk about their volumes, I would use this ratio to compare their figures, the two figures. All right, so we're being told in this particular problem that the surface area of the smaller figure, remember, is 192 square meters. Okay, so let's compare the surface areas. That's an area, a measure of area. So I'm going to use 16 over 81 and say, okay, the smaller one was, let me just double check again, was 192. So that goes over here. Does it go on top or bottom? Well, they said it's the smaller figure. Is 16 or 81 smaller? 16 smaller. So it corresponds to the 16. And I'm trying to find the surface area of the larger figure. So this is the surface area. Sometimes we say SA for that. This is the surface area of the smaller. I need the surface area of the bigger. This is my ratio or my proportion that I'm going to solve. And I'm going to solve it by cross multiplying. Let's call this X. When I cross multiply this way, I get 16 times X. When I cross multiply this way, I get 81 times 192, and that's 15,552. Divide both sides by 16, and X is 972. Now this is the surface area of the larger figure. It was in meters. This was square meters, so this is square meters. Okay, that's the surface area of the larger. Then they asked me to do the same thing, compare their volumes. To compare their volumes, I won't use an area ratio, I'll use a volume ratio. So I'm going to set up a different ratio, 64 over 729, and they could have given me the larger figure's volume, but they chose to give me the smaller volume. It says the volume is 1,536 cubic meters. Okay, Smaller means I'm going to put it on top. Why? Does smaller go always on top? No. This is smaller, that's why. It has to correspond. It has to go with the corresponding measure. This is telling me 64 to 729 is the ratio of the smaller volume to the larger volume. Okay, so I need to, let's go ahead and put the x in from the start. When I cross multiply, I get 64x equals, and I'm going to go ahead and do 729 times 1536. Woo, big number. 1,119,744. 119,744. Now I divide that by 64, and I get 17,496. This is volume. We're in meters, so that would be cubic meters. And that's the volume of the larger figure. And I probably shouldn't have used X for each one, so maybe you want to use Y for this or something like that. But I was just using it for a moment to find the missing value. Okay, that's my excuse, and I'm sticking to it. I hope this video has helped you and you are able to fly through your problems on similar solids and their surface areas and volumes and how they relate. And I will see you next time. Thanks so much for watching.